So in order to find that that difference is actually bounded by a constant, we are first going to split this difference into a sum of different terms, where each term is the difference between two hybrid machines that go on for a certain number of steps as a prop machine, and then from then on just go linearly through the expected numbers, and then they're allowed to use numbers that are not integer. So that first sum is, each term is telling us how much difference does one time step of a prop machine make in the difference of the numbers that we're looking at. And then we can further split that into another sum of the influence of just one position at one time that gets a prop step instead of a linear step. So in the next slide I'm going to explain more what this influence means, but it's just supposed to be really what difference does it make that one position at one time use the prop step instead of a linear step. And then we just change the order of the sums here, to sum in y first and in t later, no, first in t and then in y. And what the goal is going to be throughout all the calculations to show that that internal sum, the one in t, for a fixed y is smaller than y to the minus 2. Because then when we sum that over y, then we get a constant. This is going to be the main thing that we're going to be doing, is take a sum in t for a fixed y, and then that sum has to be less than y to the minus 2. And then we sum that over the y's, and that gives us a constant. That's what's going to happen. So, okay, so let's take a look at this influence thing to see what it looks like. Here is the origin, and this is the probability that a chip in this position will get to the origin in time 1, because we only have one time here. So from here we have a half probability of getting there, because we could also get here. From here we have 0 probability of getting there, because it's just too far away. And if we define this function hyt to be just the probability that a chip in position y gets to the origin in time t. So this is what I'm writing here. And of course, we have something like h here is half of this plus half of that, right? Because from here we have half chance of going here and half of going here, so it's basically, it's just an expected value. So h minus 2 is 1/4. The influence goes like this. After you take a prop step, this chip that started here is not half here and half there. It's either all here or all there. So, and it makes a difference what the arrow was, where the prop step actually took the chip. So for now, just for this slide, let's say the influence to the right and the influence to the left. In the following slides, I'm just going to suppress all that notation because it would get very, very messy. But right now, the influence of a prop step to the right over a chip at position minus 2 that has 2 time units to get to the origin is, well, take that prop step to the right and look what is the probability that it will get to the origin now, and subtract from that the probability that it had of getting to the origin before. So what difference did this prop step make? It made 1/2 minus 1/4, so influence to the right of minus 2 is 1/4. The influence to the left, if the arrow was pointing this way and sent the chip here, so now after the prop step I have 0 chance of getting to the origin. Before I had 1/4. So the influence to the left here is negative 1/4.